Today we are going to discuss about coagulation aided sedimentation. See the word itself, it says coagulation aided sedimentation. Means coagulation is there and after that sedimentation, again that chapter comes. After doing some process of that coagulation, again that sedimentation chapter comes. Therefore it is called as coagulation aided sedimentation. Then just we will go back. In screening, what we do, we will remove floated materials, floated particles. For example, trees, bushes, leaves, debris, they we will remove in screening. And after that, which are escaped from the screens, smaller materials, but the specific gravity is more than the water. Those are removed in sedimentation. Why? Because they have a specific gravity more than the water. If we retard the velocity, then definitely in due course of time, that time is called as a detention period. Within that detention period, 4 to 8 hours, then those particles automatically, due to gravity, they will come and settle to the bottom. But still smaller particles will be there. Small particles means even though you leave it for many hours, but they never settle. Best example is your colloidal particles. For example, milk is there. Milk is made up of white pigments will be there. They are called as colloidal particles. Your toothpaste is there. Inside the toothpaste, some white color will be there, but those particles are colloidal particles. And foam is there. When you that use a soap and you will get a foam, that foam is again the colloidal particles. These particles, they never settle down. We need to forcibly make them to settle down. Therefore we have this chapter, that is a coagulation. Understood? Such colloidal particles, they are harmful for the human health. They are also available in the water. Those particles we need to remove from the water. Understood? Then now we will understand the mechanism, how it operates. In brief, I am going to tell you that colloidal particles are negatively charged. They are negatively charged. Colloidal particle surface will be having a negatively charged signs, that is minus. Understood? And the surface charge on colloidal particles give them long-term stability. It will give them long-term stability. Therefore, they never settle down. And one colloidal particle and the other colloidal particle, they never attract each other. Why? Because both are negatively charged. Like that, number of colloidal particles which are there in the water, they all are negatively charged. Therefore, they never attract each other and their mass will never increase. Therefore, they never settle. Understood? Now, what we need to do? We need to destabilize these particles. Destabilize means what? We need to build one surface layer on the colloidal particle. Colloidal particle is there, negatively charged is there. We need to make one surface on the colloidal particles. When we make a that one surface on the colloidal particle, that thin surface we will call it as a rigid or stern layer. Understood? Now that rigid and stern layer, when it attached to that colloidal particle, then there will be a drop in the potentiality. That drop in the potentiality is called as stern potential. Then after that, another layer which will come and attack to that stern layer because of added water, then that layer is called as diffuse layer. In that diffuse layer, again the potentiality decreases. That potential is called as a zeta potential. Therefore, the complete particle, the colloidal particle, which has a much more potential, that is a negative charge, but because of this stern layer and this diffuse layer, that potentiality decreases. Now the colloidal particle is surrounded by some gum-like structure. Gum-like layer is there. That layer will attract the smaller particle towards it. Understood? these smaller particles, and they come and stick to this colloidal particle, that is coagulated colloidal particle, and the mass of that becomes more, and that when that mass becomes more, that particle will come and settle by gravity. Understood? Once again I will explain. Colloidal particles are negatively charged. Many colloidal particles are there, they are all negatively charged, therefore they repel each other. We are adding some chemicals into the water. Those chemicals are called as the coagulants. When we add a coagulants to the water, those coagulants make one layer on the colloidal particle. Those layers are called as a rigid layer and a diffuse layer. These layers having a gum in nature, that is called as agglomeration, and this agglomeration which will destabilize the material, and this start attracting the small particles, small other colloidal particles and small soil particles that will attract it towards this particle, colloidal particle. Then the weight will increase, therefore the size will increase, and that increased size with the increased weight will settle down due to gravity. This is coagulation. Technically, here we have few terms. The first one is a coagulants. Coagulants are chemical compounds which are used for coagulation purpose. Next technical term is flux. When we add a coagulants to the water, when we mix them thoroughly, then there a gelatinous precipitation appears. That gelatinous precipitation is called as a flux, and this process is called as flocculation. The entire process, adding the coagulant, mixing and preparing making a flocculation, this entire process is called as coagulation. When coagulation completes, then again we will give some detention time there, but it is a very lesser than the sedimentation detention time. Then in that detention time, water is allowed into the sedimentation tank. Again it comes there. In the sedimentation tank, they all come and settle to the bottom and they are removed. Now chemicals used for coagulation. There are 4 types of chemicals used in coagulation. The first one is alum, and the second one is copperas, and the third one is chlorinated copperas, and the fourth one is sodium aluminate. We will explain them in details. Now the first one is use of alum as a coagulant. See, this is my favorite topic. Why? That I will explain when I come to the problems. Okay, now look at here. The first one is use of alum as a coagulant. Then what is alum? Alum is also called as a filter alum also, but actually its chemical formula is Al2SO4 18H2O. See this reaction. Alum is mixed with 3 calcium bicarbonates and produces 3 calcium sulfate and 2 aluminum hydroxide precipitation and 6 carbon dioxide which evaporates. This is a balanced equation. You need to mug up this one. There is no alternate. You need to mug up that one. Look at here. Alum is mixed with 3 parts of calcium bicarbonate. Then where this calcium bicarbonate comes here? There will be water, no? To water we are adding alum. Then where will be this calcium bicarbonate? Calcium bicarbonate will be there in the water itself. Water, sometimes it is alkaline, and now this sedimentation and coagulation, it is just a second part of this water treatment. Therefore the water is raw only. Therefore in the raw water itself, the calcium bicarbonate will be there, and the alum added, it will react with calcium bicarbonate present in the water itself. Then it will produce calcium sulfate, aluminum hydroxide and carbon dioxide. The second question is, if the water doesn't have calcium bicarbonate, then what? If the water doesn't have calcium bicarbonate, then it might have calcium hydroxide. Then the reaction follows like this. Alum reacts with the 3 calcium hydroxide, then produces the same 3 calcium sulfate, aluminum hydroxide plus 18H2O. Then okay, the third question is, if that is also not present in the water, then it may contain sodium carbonate, Na2CO3. Then the reaction goes like this. Then alum, 3 parts of sodium carbonate, and that produces 3 parts of sodium sulfate and 2Al2OH thrice, 3CO2 and 15H2O. It will produce. Then again the question comes, fourth question. If this is also not there in the water, see, calcium bicarbonate, it must be there to happen this reaction. Calcium hydroxide alternate, it should be there. If that is not there, then sodium bicarbonate should be there. If that is also not there, then what to do? Then you need to add externally that content to the water, that is a calcium, that we will call it as a lime. We need to add lime to the water. We need to generate that calcium bicarbonate or calcium hydroxide inside the water, so that this reaction happens. Means to happen this reaction, calcium bicarbonate or calcium hydroxide is a compulsory. It should be there in the water, or you need to add externally to the water. Understood? Now we will understand one more phenomenon which is discussed in the second module, that is your alkalinity. We'll go back and come here. Alkalinity is always because of 3 parameters: carbonates, bicarbonates and hydroxyl, OH, HCO3 minus, CO2, CO3 minus minus and OH minus. Because of these 3 compounds, and these 3 will mix with some other compounds, and that will be, there will be alkalinity in the water. Okay. When we add alum to the water, then the water should be alkaline. Okay. Then alkaline, that too with calcium bicarbonate. Understood? Alkalinity due to bicarbonate, alkalinity due to carbonate, alkalinity due to hydroxyl. Out of these 3, alkalinity due to bicarbonate and alkalinity due to hydroxyl should be there in the water to happen this reaction. If it is not there, then you need to make that to happen. Okay. Now when we will get, every time we cannot do experiment whether alkalinity is there or not, okay, and checking this one every time, it is time consuming. Therefore we have a scale here, that is a pH. Now look at here, we have a pH from 1 to 14, and alkalinity test, it says that if the water has a pH more than 10, then the alkalinity, that is also alkalinity, that alkalinity is due to OH. If the water's pH is from 10 to 8.5, then the alkalinity is due to OH alone or carbonate alone or OH and carbonate together. Understood? If the pH value is less than 8.5 and more than 4.5, then the alkalinity is due to bicarbonates only. Bicarbonates only. Bicarbonates, their H is there, no? Means it is coming towards acid side. Therefore that H will come and add to that carbonate, and therefore that alkalinity is due to bicarbonate. Understood? Now means to happen this alum reaction inside the water, then the pH of the water should be 8.5 to 4.5. If the pH value is less than 4.5, then you don't get any alkalinity. Even there is a carbon and oxygen hydrogen is there, but that forms carbonic acid, not alkalinity. Therefore, our pH value should be 8.5 to 4.5. Some textbooks say 8.3 to 4.5. Next is to happen this coagulation process very quick and very effective, then your pH value should be 8.3 to 6.5. 6.5 means we will have a 100% assurance that only bicarbonate present in this one 4.5 6.5 to 8.3. Therefore the pH should be maintained like that. Means here we can give one general statement that the coagulation alum will be very effective when the water is alkaline, when the water has a pH 6.5 to 8.3. Okay. Now again we'll see the reaction. Alum is added with the 3 parts of calcium bicarbonate. Then what it gives? It gives 3 parts of calcium sulfate. Now see this calcium sulfate, can you recall something in second module? Give a hint. I will give a hint. In second module, come to the chemical properties, hardness. Yes, in hardness we have two types, temporary hardness, permanent hardness. Yes, permanent hardness, sulfate, calcium and magnesium of sulfate is there. Therefore you can recall that one. You can see here calcium sulfate means it is generated. Alum is added with the 3 parts of calcium bicarbonate and it gives 3 parts of calcium sulfate, means permanent hardness is induced inside the water by adding alum. Demerit. Next, it produces 2 parts of aluminum hydroxyl. Yes, hydroxide precipitation. Aluminum hydroxide precipitation is the precipitation which is exactly required for us. That is called as a flock, and that starts attracting your small particles, and that size increases, and there that particle size increases and that settlement happens. Therefore the reaction whatever we are adding alum here to produce, our main intention is 2AlOH, thrice aluminum hydroxide precipitation. This is a very important parameter for us. Then after getting this one, this will be flocculate, this will is a precipitation, and after that we will get 6 parts of carbon dioxide. Now again go to the second module, chemical properties, dissolved gases, CO2. In there CO2, when it is there in the water, then there will be a corrosion in the pipes. This is some demerit. Means by adding alum, sedimentation, of course sedimentation process becomes effective, we can remove many particles, but the demerit is permanent hardness increases and corrosion problem arises because of 6CO2. But of course it will evaporate, but still the water will be having some CO2. This is somewhat dangerous with respect to alum, but alum is very good product and cheaper in market. The value, the cost is very cheap compared to other. Understood? Therefore we are preferring alum. And if the water is somewhat very clear, then the dosage you can use 5 mg per liter. If it is very turbid water, then 85 mg per liter, maximum 85 mg per liter you can use as a dosage. Understood? But in an average 17 mg per liter is used for coagulation purpose. Okay, means the dosage is depending on what? Dosage depending on the turbidity of the water, concentration of suspended particles. Okay, now this we will identify in the laboratory. There is one column test is there. In that test we will do this one and we will identify how much dosage is required. Understood? Okay. Now how to use this equation practically I will explain later. Next, second chemical coagulant is copperas. Copperas means it is a ferrous sulfate. Chemical name is FeSO4 7H2O. Okay, now the reaction is like this. Copperas reacts with hydrated lime, CaOH twice, and it produces calcium sulfate, then ferrous hydroxide, and 7H2O. Okay, now this is one reaction. If the water has a CaOH twice inside, then this reaction will happen. If the water doesn't have a CaOH twice, if the water has a calcium bicarbonate, then this reaction will happen. That is ferrous sulfate, calcium bicarbonate, then it produces FeHCO3 twice, CaSO4 plus 7H2O. Now this FeHCO3 twice again reacts with CaOH twice. Then it produces FeOH twice, 2CaCO3 plus 2H2O. Now here in the first equation and second equation, in the first equation one reaction took place and we got ferrous hydroxide. And in the second reaction, two reactions took place and there we got in the last reaction ferrous hydroxide. Either that reaction or this reaction, this ferrous hydroxide again reacts with O2 and H2O and it produces ferric hydroxide precipitation. Now our aim here is ferric hydroxide precipitation. This is a very important compound for us. This will act as a flock here. Understood? Now, based on the availability of CaOH twice and HCO3 twice, the reaction two reaction happened, but ultimate aim is ferric hydroxide, FeOH thrice. Understood? Then again by adding copperas, again the permanent hardness induces. Okay, na? But that CO2 problem is not there here. Now chlorinated copperas as a coagulant. Then what is chlorinated copperas? Okay, we will not get that one. To get that one, what we need to do? Copperas, the earlier agent, that copperas is mixed with 6 parts of copperas mixed with the 3 parts of chlorine. Then it will give ferric sulfate and ferric chloride. This ferric sulfate and ferric chloride together it is called as chlorinated copperas. And out of these two, one react with the hydrated lime and it produces ferric hydroxide precipitation that was required for us. And the other one again reacts with hydrated lime and it again gives ferric hydroxide precipitation. Again it was required for us. Okay, likewise we are getting flock here, FeOH thrice. Ferric sulfate is quite effective in 4 to 7 and above 9, and whereas ferric chloride is effective when pH is 3.5 to 6.5 and above 8.5. The combination has therefore proved to be very effective coagulant for treating low pH water. Understood? Now very interesting fourth coagulant, that is sodium aluminate. And the sodium aluminate, the chemical formula is Na2Al2O4. This sodium aluminate reacts with calcium bicarbonate and produces calcium aluminate, CaAl2O4 and Na2CO3, CO3H2O. Then it can again, that sodium aluminate again it can react with the CaCl2 and it can produce CaAl2OH4 and 2NaCl. Then again if that is not there, then a sodium aluminate can react with calcium sulfate and it can produce CaAl2O4. Here calcium aluminate, CaAl2O4, is our flock. It is used for sedimentation. It helps in sedimentation. Now, very interesting thing here is, if the water has alkalinity of bicarbonate, then sodium aluminate will react with that and it will produce its compounds, that flock. And if alkalinity is not there, then only it will act as a coagulant, means it is some positive thing compared to alum. Alum is only when it is alkaline, then only that reaction takes place. But here alkalinity is not there, then also sodium aluminate can react and produce flock. Now one more advantage here is, if any permanent hardness like CaSO4, then it will react with the permanent hardness and it will produce a flock, as well as decreases the permanent and temporary hardness. Therefore, sodium aluminate is a somewhat very good coagulant. The positive compared to alum is, it doesn't require alkalinity and it reduces permanent and temporary hardnesses. But the disadvantage is, this is 1.5 times, means 50% more costlier than alum. Therefore, we avoid this sodium aluminate. Then where we can use this one is, where a boiler feed water, if you want to treat, there you can use, because the corrosion or incrustation in the boiler is avoided due to hardness or due to increase in the CO2. If we want to reduce that effect, then you can use sodium aluminate as a coagulant. Okay, some advanced treatment plant you can use sodium aluminate. Otherwise, alum is good for us and universally accepted. Then the comparison of alum and iron salts you need to do. The general here is, alum is used for water treatment and iron salts are used for sewage treatment, and rest other some 3 to 4 points you do it by your own. Thank you. Today we are going to know about constituents of coagulation sedimentation plant. Means what all units are there in the entire coagulation sedimentation plant, or you can say what all steps involved in this entire coagulation process. This is divided into 4 main heading, that is units. The constituent of coagulant sedimentation plant units are divided into 4 parts. The first one is feeding devices, and the second one is mixing device or mixing basin. Third one, flocculation tank or flocculator, and the fourth one is settling or sedimentation tank. These 4 are there. Just by seeing their names only you can understand what all the process that includes, the entire process includes. That is, feeding device means the chemicals which we have, they are called as coagulants that we are going to feed into the tank. And a mixing device means what? Those chemicals added to the raw water and there it is mixed with the raw water. In the flocculation tank or flocculator means what? There it is allowed for, there is a slow mixing process will be there, so that there that flocks can generate. And the last one is, we are going to allow them to settle down, that is your sedimentation tank. We will go one by one. Feeding device. Here we are, as I said, that here we are going to feed chemicals, that is your coagulants, and availability of chemicals may be in 2 types. The first one is chemicals may available in powder form or they may available in solution form. Okay, if you are feeding powdered form, then we will call that as a dry feeding, and if you are feeding the solution form of coagulants, then we are calling it as a wet feeding. Means we have got 2 feeding devices, 2 types. Okay, means which one we need to select? There is a question, right? Which is suitable for our project? How to select that one? We have 4 factors here which affects the selection of wet feeder or dry feeder. The first one is the characteristics of coagulant and convenience with which it can be applied. Means the property of the chemicals will guide us whether we need to go for wet feeding or dry feeding. For example, alum is a fairly finely divided particles will be there. It is uniform in size. Then these powders can be taken in a uniform in size means what? They will be available in powdered form only. Those powdered form you will take it and you will feed it into dry feeder. Okay. For example, another some chemicals like copperas is there. This copperas is not a this uniform in composition. It don't have a uniform composition, which clogs when it come in contact with the water there, and it may become a sticky mass, okay, solid. Therefore such we need to take in wet feeding only. Okay, this is the first characteristics. Second characteristics is the amount of coagulant to be used. How much quantity you are using for your coagulant, that also matters. For example, if your quantity to be added into the coagulation tank is very small, then what you need to do, you need to take that small quantity and make a solution, and that solution can be added into the coagulation tank, so that that small quantity can be spread each and every corner of the coagulation tank. Therefore when the quantity is very small, then solution form means wet feeder can be preferred, and when the quantity is very huge, then you can prefer dry feeder. And the third property is cost of the coagulant and the size of the plant. See, if the plant is very big in size, then first I would like to tell you that dry feeding and wet feeding, here the wet feeding is somewhat accurate, somewhat good, it will give a good result, but it takes it is very costly also. When you are thinking of a big project, like size of the plant is very big and the cost involved in the coagulation plant is very big, then you will not worry about the small feeder, that how much it takes a cost, that one. Therefore when the plant is very big, then you can go for wet feeder. If the plant is very small and very less water is treated there, then you can go by dry feeding. No need to spend money on that one. And the fourth property is, in wet feeding equipments, in addition they require making and preparing solution for a required strength. Therefore for this one you require somewhat skilled laborers or skilled person to handle these all things.
Now we will go through dry feeding device. Okay, in this device we already got dry feeding and wet feeding. See here, it is a type, it is somewhat conical in shape, and the bottom there is a tooth wheel is there. This is a tooth wheel. I mean some wheel will be there here, and this entire thing is a powder. That powder is kept here. And this dry feeding we have two types. One with a wheel here, and another with a helical screw here. Okay, we have two types of feeding device. And this is called as a hopper. This conical shape wall is called as a hopper, and inside a small plates are there. You can call it them as a blade. Why? Because this continuously rotates. This continuously rotates like this, so that if any powder is stick to the wall of this device, then it can be removed. And this tooth wheel is used to regulate the flow of this powder. Okay, and if you increase the speed of the wheel, then it comes very fast. And if you can regulate the flow of the feeding this chemical to enter into the mixing basin, that is the next step. And this regulating can be done by the wheel, or it can be done by pulley arrangement also. Okay, the helical screw is there. You can rotate this one so that the powder will start coming down and entering into mixing basin. Okay, this is what your dry feeding device. And the second one is a wet feeding device. It's very important. Here we have so many, again a small units are there. We can go through here, regulating coagulation solution inflow. Here we will be having one big tank. There the solution form of coagulant will be there. Solution form will be there. Then the uniform strength is achieved here, and that is called as your regulated coagulation solution inflow. This valve will control the inflow of that one. Then it is coming here, and this chamber is called, this tank is a constant head coagulation feeding tank. Here the head is maintained constant, therefore it is called as constant head coagulant feeding tank. And that whatever the solution, that solution comes like this, and it enters into here the raw water. The raw water is coming from here, and that raw water comes here, and the powder, the solution comes here, and it will be mixed. This is a mixing basin. That how this mixing basin will be, that I will explain later. Then here one more chamber is made, this actually it don't have any function in the coagulation process, but it is to regulate this unit. Okay, to regulate the flow of coagulant from this chamber, we have used this floating. Just to go through here. Now see, here one vertical plate is there, and it comes like this, and there is a here ball is there. This is called as a floating ball, just like your WC. Okay, in bathroom, in a flush, you can observe such a that arrangement. That is your ball will be there. Means when the water comes to rises here, the head rises here, this floats upward, and when it floats upward, then it can come and it can lock your inflow of the coagulants. Means when the water is completely to the top level, then it will rise and it will close the valve. And if the water comes to the down level, then this float will come down, then this valve will open. Instead of this valve will open. And this is one type of regulating this inflow of coagulant. And the outflow of the coagulant, this how to regulate this one. Because it will be stored here, and after that one how to allow this we need to think. Therefore here this arrangement is made. This is called as a floating chamber. Float chamber and the mixing basin, both will be made with the same level of water. Same level will be there. How? Because it is connected here, interconnected. Therefore, and here one float is kept here. As the water rises here, then this float with this string will rises. And here an arrangement is made in such a way that I will leave it to you only to decide how it is arranged. And when it rises here, then this string, this rod will send a message here, and this will be pulled up. When this is rises up, then this is pulled up. Then when this is pulled up, you can come here, that is connected to here, that is called as a conical plug. Conical plug means if it is your opening, then the plug is like this. This is a conical plug. That will be regulated. Why this arrangement is made? Because if your raw water inlet is more, then what it indicates? It indicates that the floating chamber water is increasing its level. When the floating chamber increases, it sends a message to this conical plug, and it will be lifted up. Then more amount of water that coagulant can be mixed. The raw water is more, then the coagulant mixing will be more. And this is accurately measured, that what maintained, that how much dosage is required, in that basis it is maintained. This is your wet feeding device. Now we are understanding the mixing device and how it will be, how that arrangement will be there in the mixing device. Mixing device means we don't have any mixer here. We have two types of mixing device. The first one is mixing device with the baffle valves, and the second one is a mixing device equipped with a mechanical device. Mechanical device understanding is very easy. Just go through this one. Electric motor is connected here, and the water which enters here, raw water, this inlet of raw water comes here, and this comes like this. Here small one valve is made. That is deflecting valve. Water is deflected from here, and it will come from here. So that here some more amount of turbidity will be created, so that it helps in mixing. Then here one impeller is there. You can call that it will rotate in this direction by this electric motor, and the coagulant pipe from the feeding device, that coagulant enters here from the feeding device. It may be a wet or otherwise dry. That will come from this pipe, and it comes here only where the impeller is rotating. Then it continuously rotates, and this will mix with the raw water, and mixed quantity will come out as a come out to the flocculator, that next unit. This is what your mixing device equipped with mechanical devices. And we have another mixing device with baffle valves. See here we don't have any electric motor and all, but the plant itself it is arranged like that. Here there is one valve, that is an inlet for water and coagulant. Water and coagulant both will come to here, and see, you can see the water comes here, and it goes in this direction, in this direction, in this direction, and in this direction. And everywhere, whenever it goes, whenever it turns to get a direction, there a lot of turbidity will be, lot of turbulence will be caused. A lot of turbulence will be caused. That turbulence will make this chemical to mix into the water effectively, and after that it will come into the flocculation tank. Understood? This is called as a plan of around the end of baffle type. Okay, and this is horizontal flow type. This is a plan. We are seeing it from top view, and this is a mixing device. And we have another type of baffle mixing type. Here the water is coming here. This is the elevation, not a plan. The baffle valves are vertical here, and another one. The water comes vertically down here and up here and down here up here. Like that, water is taking its path, and again the turbulence will create here. That helps us to mix the coagulant effectively. Understood? This is your mixing device. Then next, after mixing these all that water and chemical, then that will go to the flocculation chamber. Flocculation tank. Here flocculation tank means what? The chemical reaction exactly happens here, and the turbidity is also there, means some suspended particles, colloidal particles are also there here, and the chemical with raw water it is coming here, and here some pedals arrangements are there. Okay, and they will be rotating very slowly.
Okay, therefore it is called as a slow mixing technique. Therefore they are slowly that rotating, and in that time that chemical reacts with water and the suspended particles, and it makes a flocks here.
Okay, and those flocks will allow to go out of this box, that is flocculant tank, and they go to your sedimentation tank. The sedimentation tank, we already know that one, how it will be. That you can see here, this flock from the flock chamber, the water is that flocks are coming here, and they are allowed that some detention time will be given here, and slowly the water will be moving from here to here. Then due to gravity, they all will be settled here, and those will be removed. They are called as sludge. They will be removed, and the clear water can come out of this one, that is the outlet channel. This may go to your filtration unit. The entire coagulation tank, you can see here, inlet, water is entered here, flash mixing is there. here mixing device is there, and that mixed water and that will come to your this water flocculation chamber, and here pedals are there and slowly they are rotating, therefore the reaction is happening, and after that settling basin is there. This settling basin, here it is considered circular settling tank, but here it is considered rectangular settling tank. Anyone can be used, and that water will come here and goes to filter. This is what your coagulation sedimentation plant, coagulation and sedimentation plant. Over. Today we will understand this one, and tomorrow, in the next class, we will study the problems, that design problems, or that chemical relations, how to use that chemical reaction. Those problems also we will see in the next video. Thank you.
Coagulation and sedimentation tank. Okay, and this lecture is going to become very heavy because we are solving about 7 problems here, and before seeing this one, just go through the chemical equations and chemicals, coagulant chemicals, and even if you want you can go to the sedimentation tank design and all of them, so that this chapter becomes very lighter. Now come here. Here I would like to explain first how to analyze the problems, and later we will solve some problems. In coagulation tank or coagulation cum sedimentation tank, we are going to get 2 type of problems. The first one is problems on some dosage or otherwise some chemical reactions, problems on chemical reactions, and another type of problems we are getting purely based on design. Design means not structural design, that is RCC and steel design. Here only the dimensions of the tank we are going to decide, that is called as a design, and problems on the chemical properties or chemical reactions that we are going to see. And to solve this chemical reaction type of problems, we should know some basics, and these basics you might be gone through when you are PU, or otherwise even 10th also they will be there, and even in basic science you might be gone through, but still I am going to recall all of them. See here, this is a periodic table, as you already know. In this periodic table, the first the nomenclature is, here it is said that how to read the periodic table. Here the number will be given and the symbol will be given and the name of the element and mass of the element. Okay, and one thing, be clear that I am not a chemistry teacher, I am a civil engineering teacher, therefore I am going to draw the chemistry part from chemistry, that much only, which is exactly required for civil engineering. Okay, I don't know the exact reason behind the chemical reactions and all, but how much it is required for civil engineering, that I am going to surely give you. Okay, see here, in water we will be observing some chemical compounds, chemical elements. They are hydrogen, and coming to the sodium, magnesium, and potassium, calcium, and this one, and coming to like that there are many are there. Aluminium is there, and silicon also sometimes in turbidity only will remove it. Like that there are many elements, carbon. Okay, many elements are there. Those elements will be there in the water, therefore I have listed them here, elements, those elements, and this is this table, this column indicates the name of the element and the symbol used for that, and this is a molecular mass. And one more, actually I required this one more, that is equivalent weight of the each element, or otherwise equivalent weight of the compound. Okay, but that I did not include here because in this chapter that is not required, and wherever it is required I will bring it. Okay, now this is hydrogen, and hydrogen symbol is H, and its molecular mass is 1. And molecular mass means what? In chemistry you should be knowing that the whatever we measure, we don't measure it in terms of gram or in terms of kg and all. We will be measuring always in terms of moles. Okay, 1 mole means what? Okay, if you go to the any general store and you can ask 1 kg sugar, right? 1 kg sugar you can get it, but when you go to the chemistry store, there you cannot get 1 kg hydrogen. You need to tell them that 1 mole of hydrogen. Then this 1 mole of hydrogen will be having some that convention, and they will convert it and they will give you 1 mole of hydrogen means what? That much they will give you. That is what I am going to convey here. The 1 mole of hydrogen means it is 1 gram. Like that, carbon, this is 1 mole of carbon means this is a 12 gram. Like that, nitrogen 14 gram, oxygen 16 gram,
sodium 23 gram, and magnesium 24 gram, aluminium 27 gram, sulfur 32 gram, chlorine 35.5 gram, and potassium 39 gram, calcium 40 gram, magnesium 55, and ferrous 56. This last one is copper 63.5.
We have many, actually speaking 114 or 104, 108 something, some elements are there, but which are there for our water treatment plant, which will help us in water treatment plant, those only listed in the table. And now come to the chemical compounds. This is the individual elements till here, and now OH is it is called as hydroxyl. Hydroxyl is a OH and its molecular mass is 17. Why it is 17? Because oxygen is 16 plus hydrogen is 1, therefore that is your 17. Then water. Water means you already know, that is H2O. H2O means what? Hydrogen 1, there are 2 hydrogens, 2 plus oxygen 16, therefore it is 18. Understood? Now carbon monoxide. Carbon monoxide means CO. Carbon is how much? 12, and monoxide, oxygen, 1 oxygen 16, therefore it is 28. And carbon dioxide, CO2. Carbon is how much? 12 plus oxygen is 16, 16 into 2 is 32, that is your 44. Then carbon trioxide. Carbon trioxide we also call it as a carbonate ion. Okay, therefore this is very important. Okay, very important for water treatment. Then CO3 is what? Carbon is 12 and 16 3s, it is 48, and 48 plus 12 is 60. Then calcium carbonate. Calcium and carbonate. CO3 is a carbonate and this is a calcium carbonate. Calcium is 40 plus carbon is 12 plus oxygen 16, and 16 into 3, that total it is 48. 48 plus 12 60, 60 plus 40, it is 100. Then calcium bicarbonate, HCO3 twice. Okay, CaHCO3 twice, calcium bicarbonate. Only bicarbonate means what? This is bicarbonate. This only bicarbonate means this is a 61. Why? Because carbonate is 60 and 1 61, and 61 into 2 plus 40, that is your 162. Okay, then calcium oxide. Calcium oxide, it is also called as a quicklime. You should remember this one. This is a quicklime we will call. The chemical formula is CaO. CaO is a calcium oxide or quicklime. In the problem they mention it. Its weight is 56 because 40 plus 16, 56. Then calcium hydroxide. Calcium hydroxide. This is OH. CaOH twice. You should be knowing this one, that Ca valence is 2, therefore that will come here, and OH valence is 1, and that will come here. This this check you should know, otherwise you mug up the chemical formula. Ca and OH twice. Then Ca is 40, OH is 17, 17 into 2, 34, 34 plus 40, that is your 74. Then alum. Alum is what? Alum is Al2SO4 thrice, 18H2O. Then here you just take all the molecular mass, they are already there in the list, and by taking that Fe56 SO4 96, 7 into 18, then you will get 278. This is your ferrous sulfate, and alum is Al2SO4 thrice, 18H2O. Then ferric sulfate. Ferric sulfate is FeSO4 thrice, Fe2SO4 thrice, Fe2SO4 thrice, you are getting 400. Then calcium sulfate. calcium sulfate is CaSO4. CaSO4. This is calcium sulfate, that you are going to get 136. Aluminum hydroxide, AlOH thrice. Okay, AlOH thrice, that you are going to get a 78. Then ferrous hydroxide. Ferrous and ferric, very important. Wherever this ric will come, no, ic means it is a 3, and us will come wherever that is a 2. It is my convention. Therefore, ferrous hydroxide, this is FeOH twice. Okay, that works 90. Then ferric hydroxide, FeOH thrice. FeOH thrice. Then ferric chloride, then FeCl3. That is ferric chloride. Then sodium aluminate. Sodium aluminate is Na2Al2O4. Na2Al2O4. That works to 164. Then calcium aluminate, CaAl2O4, that is 158. Sodium carbonate, Na2CO3, 106. Calcium chloride, CaCl2, calcium chloride, 111. Then sodium chloride, that is NaCl, that is 58.5. You just cross check them so that you will get a practice also, and you should remember these names and these formulas and those molecular masses. They are very, very, very useful, not only in this chapter, even in many chapters. Chemical reactions and understanding the basics of chemical reactions is very important in water treatment engineering. Okay, that you should keep in mind. Okay, now some reactions in the second video, that in the coagulations second video we have already gone through. That is 4 coagulants were there: alum, copperas, chlorinated copperas, and sodium aluminate. These 4 chemical compounds, they are coagulants, and those reactions also explained in the that last video, last video. And now I am going to recall, which is very important for water treatment, because in coagulation chapter only, in coagulant, while explaining coagulant only, I told you that alum is used for water treatment and iron salts are used for that wastewater treatment. Therefore, my concentration is only towards alum, and same thing you need to work for other chemical reactions also. Okay, now coming to here, this is the reaction alum. This is a complete alum, and this alum is mixed with 3 parts of CaHCO3 twice, and it gives 3 CaSO4 plus 2 AlOH thrice plus 18 H2O plus 6 CO2. Now, how to read this equation, that is very important. Reading this equation is not like that how I read here. The reading is like this: 1 mole of alum requires or consumes 1 mole of alum consumes 3 moles of calcium bicarbonate, and it produces 3 moles of calcium sulfate, 2 moles of aluminum hydroxide, 18 moles of water, 6 moles of CO2. 6 moles of CO2 evaporates, and this is called as a precipitation, that is your flock. And this you already know, this is SO4 is there, calcium is there, this is the permanent hardness, and this is the water. Understood how to read? 1 mole of alum consumes 3 moles of calcium carbonate produces 3 moles of calcium sulfate, 2 moles of aluminum hydroxide, 18 moles of H2O, 6 moles of CO2. Here I have used unit as moles only. In the chemical reactions we should read in terms of moles only. Now, as I already told you that if the water contains this alkalinity, that is well and good. If water doesn't contain this alkalinity, then we need to produce that alkalinity. How to produce that alkalinity? See here, this is the alkalinity. If water doesn't have this one, then what we need to do? We need to take calcium carbonate, and that we need to add water to that, and we need to blow CO2, carbon dioxide. Then we will get this is CaHCO3 twice. Means 1 moles of calcium carbonate mixed with 1 mole of water and 1 mole of CO2. Then we will get 1 mole of calcium bicarbonate. Understood? But how to get this calcium carbonate? This calcium carbonate we need to get it by this one. This is CaO. CaO we will call it as a quicklime. This is called as a quicklime. Quicklime is added with CO2, then we will get a CaCO3. Understood? Or otherwise even that reaction you can show it in this direction also. Okay, now you came to know that these how they are we are going to get. Okay, and in place of, if we don't have CaHCO3 twice, then we may have CaOH twice. CaOH twice means again the reaction will be alum plus 3 moles of calcium hydroxide, and here if you don't have this one, you need to prepare this one. How you are going to prepare it? That reaction is something CaO plus H2O, CaO plus H2O. Is it okay? CaOH twice. Okay, right. Then you are getting CaO means quicklime you need to take and mix some water, then you are going to get that calcium hydroxide. Okay, this calcium hydroxide is called as hydrated lime. These technical terms are very important. Hydrated lime, calcium hydroxide; quicklime, calcium oxide, and this is alkalinity, and this is calcium carbonate. This is quicklime. Understood? Now again we need to understand them. Okay, now we are going to simplify them. 1 mole of alum means 666 gram of alum. Understood? From the table only we came to know here the alum means here, this is the alum. 1 mole of alum means 666 gram of alum. Okay, 1 mole of alum is 666 gram of alum. Okay, then 1 mole of calcium bicarbonate means what? 162 gram of calcium bicarbonate. 162 gram from the table. Understood? Calcium bicarbonate. But 1 mole of alum consumes 3 moles of calcium bicarbonate. Who said this one? The equation tells us that 1 mole of alum consumes 3 moles of calcium bicarbonate. Now 1 mole of alum means how much? 666 gram of alum consumes 3 moles of calcium carbonate bicarbonate. Then means it is 486 gram. Means every 666 gram of alum when you add, then you should require 486 gram of calcium bicarbonate should be present in the water. Means every 1 gram of alum consumes how much? 0.7297 gram of calcium bicarbonate. Now you got it, 1 gram of alum means 0.7297 gram of calcium bicarbonate. Now you can write it like this also, 1 mg of alum means what? That is also again 0.73. Okay, then 1 mole of 1 mg of alum consumes 0.73 mg of alum. Similarly, this is very important statement. Okay, this directly I can use in the calculation. Now similarly, 1 mole of alum produces, I am using produces means I am right side of the equation. then it produces 3 moles of calcium sulfate, which is a permanent hardness. Means 1 mole of alum produces 3 moles of calcium sulfate. Means what? 666 gram of alum when we add, then it produces 408 gram of calcium sulfate. 408 gram of calcium sulfate. Means the conclusion is what? Again, 1 gram of alum produces 0.6126 gram of calcium sulfate. Again, the conclusion we have made. And similarly, 1 mole of alum, 1 mole of aluminum produces 2 mole of aluminum hydroxide. This is a precipitation, also called as flock. Means what? 666 gram of alum produces 2 into 78, that is 156 gram of aluminum hydroxide. Then we can conclude here 1 gram of alum produces 156 by 666, 0.2342 gram of alum hydroxide, that is your flock. This we are going to use in the problem. Okay. Similarly, when we add when we use alum here, then 1 mole of alum produces 6 moles of carbon dioxide, and 1 mole of carbon dioxide is 44. Therefore 6 mole of carbon dioxide is 264, and 660 gram of alum produces 264 gram of. Now remember this: 264, 156. Come here to the equation. Now see, alum is how much? 666. When we add 666 alum, then it consumes 486 of calcium bicarbonate. It produces 408. Then it produces aluminum hydroxide, that is your 156. Then it produces 18 H2O, 18 times 18. Then it produces 6 CO2, 6 into 44. Now it should come, left side should be equal to right side. 666 plus 486, we have added 1152, and here we are getting 1408 plus 156 plus 18 into 18 plus 6 into 44, then 1152. Means adding together, adding all of them, then again we are getting 1152. Means it is a balanced equation. Like that we need to work for these two equations also. That I will explain in problems. Okay. First problem. Okay. First, one thing you should remember, that understanding the problem itself, solving the problem 50%. Okay. Understand. And after that, if you don't know the solution, that is good, no problem. You can search here and there. But understanding is very important. Okay. Now read the problem. Determine the quantity of alum, it's not water, alum required in order to treat 13 mld at a treatment plant. 13 mld means what? 13 million liter per day at a treatment plant where 12 ppm alum dose is required. Also determine the amount of carbon dioxide gas which will be released per liter of water treated. Okay. Now here the quantity is given now. Q, quantity of water, it is given 13 million 10 raised to 6 liters per day. Liters per day. We will keep it like this only. Wherever required, we will alter that one. Next, dosage, alum dosage is given. Alum dosage is 12 ppm. ppm I will write it as a liter, mg per liter. Then they want determine the quantity of alum required in order to treat that much. Means it's very easy. That is, quantity of alum equal to, see here, it says that 12 milligram is required per 1 liter. For every 1 liter, 12 milligram is required. Then how many liters you have? 13 into 10 raised to 6 liters you have. Okay, per day you have this much. Then this liter and this liter cancels. Then you will get 13 into 12 into 10 raised to 6. Okay. Then you are going to get 156 156 into 10 raised to 6 mg per day. These many milligrams per day, but 10 raised to 6 you can make it 10 raised to 3, 10 raised to 3. First 10 raised to 3 it came to gram, second 10 raised to 3 it came to kg. Therefore it becomes 156 kg per day. Understood? Means here this is a very practical problem, right? They wanted the total quantity, that is 156 kg per day. Next they are asking, also determine the amount of carbon dioxide which will be released per liter of water treated. Okay. First we will see the reaction. Now you check here, alum is added, 1 mole of alum added produces 6 mole of carbon dioxide. 1 mole of alum means how much? 1 mole of alum means 666 gram of alum. 666 gram of alum. Okay, alum. Then it produces 6 moles of 1 mole of carbon dioxide is 44. See here, 666 gram of alum produces 6 moles of carbon dioxide. Carbon dioxide is 44 because carbon is 12 and oxygen is 16. 16 into 2, 32. Okay, 32 plus 12, 44. Okay, now this much you got, but we will make it into 1 gram. 1 gram of alum means how much? That is your x gram.
Then x equal to 1 divided by 666 into 6 into 44. Then this comes to be 0.3964. 0.3964. Okay, 64 gram.
We will make this gram because 1 gram I have worked here. Therefore, I can make it as a mg also. Then I got
1 mg of alum produces 0.3964 mg of CO2.
Then my question is 12 mg of alum will produce how much? Therefore 4.75 gram mg per liter. Every liter it produces 4.75 mg per liter. This problem is solved. Once again go through this. In the second problem, you just see here 8 mg of copperas. Copperas means this is your copperas. Okay, this is not given in the problem. Understand that. Okay, this I have added for you. Okay, the problem is only statement, in terms of statement. 8 gram of copperas is consumed with lime. Lime it is. Okay, they have not mentioned which lime it is. We will assume it as a hydrated lime. Hydrated lime. Okay, lime at a coagulation basin per liter water. Per liter, for every per liter, then 8 mg of copperas they are going to add and some lime they are going to add. Determine the quantity of copperas and quick lime required to treat 10 million liter of water. The first problem is very easy, that is quantity of copperas. The quantity of copperas. Quantity of copperas is how much? It is very easy, no? That is 8 mg they are adding for every liter. Then how many liters we have? We have 10 million liters we have. Liters we have. Per day we have this much. Then this liter and this liter cancels. This 8 into 10, 80. 10 raised to 6, that I will write it as a kg. Okay, per day. And I got how much? 8 into 80 kg per liter. Sorry, 80 kg per day. Okay, na? That much I got. Now the second question is very important. What they are asking? Determine the quantity of quick lime required to treat the that much of water. Now see, quicklime required. Very interesting, no? Because here it is consumed with the lime, it is said, and we assume this as a hydrated lime, and even in the equation also hydrated lime is there. Copperas is added to hydrated lime. Then why they are asking quicklime? Because they don't have this hydrated lime. When they don't have this hydrated lime, they have to produce this one. How to produce this one? By taking a quicklime. Quicklime is taken and water is added, then we got hydrated lime. When we get a hydrated lime, that hydrated lime reacts with the copperas. Then it will produce these all entities. Now we don't want these all entities. We are interested in this and this. Understood? Therefore, we need to work here. Now see, what is copperas? Copperas is a FeSO4 7H2O. Then you should go back here, FeSO4 7H2O, that is ferrous sulfate, that is 278. Understood? 278. Then calcium hydrated lime, where it is hydrated lime 74. This and 278, these two you should remember. Come back here. Now see,
278 gram of copperas consumes how much? 74 gram of hydrated lime.
But we don't have this hydrated lime, but we have quicklime. Then 1 mole of quicklime, it is 1 mole of quicklime produces 1 mole of hydrated lime. Now we will consider this here. 1 mole of quicklime means what? 56 gram of CaO produces how much? 74 gram of quicklime, sorry, hydrated lime. What we want? We want the same amount. 74 gram of hydrated lime is required. Then to produce 74 gram of hydrated lime, we want 56 gram of quicklime. 56 gram of quicklime. Then we can indirectly say like this now. Then 278 gram of copperas requires or consumes 56 gram of quicklime. Okay now okay, now how much we have? 8 mg we have, no? 8 mg of copperas consumes X, then X equal to that is equal to 1.611 mg per liter. Now what they are asking? To treat 10 million liter of water. This is for 1 liter of water. Then how much? To 10 million liter of water, what we need to do? 1.611. This is mg per liter. This multiplied by 10 into 10 raised to 6. This is liter per day. Then liter cancel. Therefore 16.11 kg per day is the answer. Okay, 80 kg is required copperas and 16.11 kg lime is required. Okay, now this is all. Problem: coagulation sedimentation tank clarifies 40 mld of water. The quantity of filter alum required at the plant is 18 mg per liter. If the raw water having an alkalinity equivalent to 5 mg per liter of CaCO3, determine quantity of filter alum and the quicklime containing 85% of CaO required per year by the plant. Very interesting problem. Here something it's like this. They have given the data like this is the water, and in this water, this is how much water it is 40 mld. This 40 mld water is there, and on this water they are going to add alum, that is 18 mg per liter alum they are going to add, and they are saying that this water has some alkalinity, but alkalinity in terms of CaCO3 it is available, that is 5 mg per liter. Okay, and they have an option to add CaO. They have an option to add CaO. Okay, first we need to understand the chemical reaction. When we add alum, what happens? Okay, again the chemical reactions they don't give. Alum here it is, and it will react with the calcium bicarbonate. Is there any calcium bicarbonate information given in this problem? No. Calcium bicarbonate, whether it is there or no, not, we don't have any information. Okay, and but alum will definitely react with calcium bicarbonate only. Okay, na? But calcium bicarbonate it is not there, but it has calcium carbonate. Calcium carbonate, it will be there in the water, and CO2, if we blow something to that, then we can get calcium bicarbonate, then this reaction can happen. Okay, na? But calcium carbonate also we don't have any option to add. We have an option to add quicklime. We can add only quicklime. Okay, therefore we need to think this problem. But as per the requirements, they have asked to determine the quantity of filter alum. The first question is somewhat very easy. The quantity of filter alum they want, and the dosage it is given as 18 mg per liter. 18 mg per liter it is, and total how many liters are there? 40 into 10 raised to 6 liters are there per day. Therefore the answer will be, then it will be 720 kg, 720 kg alum. This is per day. If I want to it for per year they are asking, therefore if I multiply 365, then I will get 262.8 tons I want. Okay, the first problem is very direct and it is short. Determine the quantity of filter alum. But second question is very important. Now we need to understand, in this reaction calcium bicarbonate, alum will react with calcium bicarbonate, right? Then alum is how much? 666 gram of alum reacts with how much? 3 into 162, that is 486 gram of calcium bicarbonate. Okay, na? But we don't have direct calcium bicarbonate. Okay, therefore first we will calculate how to produce calcium bicarbonate. From this reaction I will get CaCO3 is 100, and 100 gram of CaCO3 produces 162 gram of calcium bicarbonate. Then how much I want calcium bicarbonate? 486 gram of calcium bicarbonate I want. For 486 gram of calcium bicarbonate, if you consider this X, then you will get answer 300 gram. Okay, see here, the relation is very easy. 660 gram of alum requires 486 gram of calcium bicarbonate, but to produce 486 gram of calcium bicarbonate, we want 300 gram of calcium carbonate. Okay, na? Means we can tell that 660 gram of alum requires 300 gram of calcium carbonate. Okay, na? Now 666 gram of alum requires 300 gram of CaCO3. Then 1 gram of alum requires X, and X equal to 1 by 666 into 300. This equal to 0.45 gram. Now we will make it into mg, and this also will make it into mg. Then 1 mg of alum requires 0.45 mg of CaCO3. Now how many mg we are adding? 18 mg we are adding. Then this becomes X, and X equal to 18 divided by 1 into 0.45, that equal to 8.01 mg per liter. This 8.1 mg per liter, but already water has a alkalinity, that is CaCO3, that is a 5 mg per liter already had. Therefore 3.01 extra need to add. Okay, now 3.1 what? 3.1 mg we need to add extra. But how to add? Directly we cannot add CaCO3 because we have CaO. This CaO we will mix with the CO2. Then we will produce a CaCO3. Okay, means every 56 gram of CaO will give you 100 gram of CaCO3. How much CaCO3 I want? I want 3.01 CaCO3. Then how much CaO I need to add? X. Then this X equal to 3.01 divided by 100 into 56. 3.10 it is 3.10. Work out, we'll get it 3.10. One general question I would like to ask: you want 1 kg sugar. Okay. On that day all provisional stores were closed. Therefore you went to bakery. You go to bakery and you want 1 kg sugar. Okay, but that bakery fellow says that he don't have a sugar. He says that you take a Mysore pak. Then what you do? And that logically that bakery person says that in Mysore pak there is a sugar. If you want you can take it. You just besan and sugar, you just different divide them and you will get a sugar. Then as a scientist you agree with that and you want to purchase. Now and that person says that his Mysore pak has 85% of sugar in it. 85% sugar is there, 15% besan is there. Then you want how much? You want 1 kg sugar. Then he directly is not giving 1 kg sugar, he give you Mysore pak. Then how many kg Mysore pak you take? And when you come to home, if you extract sugar from that, you should get 1 kg sugar. Then will you take more than 1 kg Mysore pak or less than 1 kg Mysore pak? You will take obviously more than 1 kg, so that the 15% will be lost now. Therefore here the same way, the calcium oxide we required, but the lime what I have, that don't have 100% calcium oxide, it has a 85% CaO. It is given in the problem. Therefore if I want 1.736 calcium oxide, but that raw contains 85%, therefore I have to divide it, then I will get 2.04 mg per liter requires. Now for 1 year I need to calculate. This is for liter, this is for 1 liter, and 2.04 into how many liters we have? 40 million liters. Okay, 40 million liters we have. This is per day, 81.6 kg per day. For 365 days, 29.78 ton quick lime required. Alum how much required? 262.8 ton. It's a very big project. This is 262.8 ton alum. Over, the problem solved. Fourth problem, the coagulation treatment plant with flow of 0.5 meter cube per second is dosing alum at 23 mg per liter. No other chemicals are being added. The raw water suspended solid concentration is 37 mg per liter. The effluent suspended solid concentration is 12 mg per liter. Sludge content is 1%. And specific gravity of sludge solids is 3.01. What volume of sludge must be disposed of each day? Based on your result, remark with reference to water treatment plant. Okay. Now this equation they don't give. You need to by heart and you need to carry. Now I will write this equation, that is alum treated with consumes 3 moles of calcium hydroxide, calcium bicarbonate, and produces these all element. You should know here, now in this problem we are concentrating on flock. How I will tell you. Okay, it is very very important. Without this equation you cannot do anything. Now see, the discharge is given. Discharge is how much? 0.5 meter cube per second. If it is in MLD, it would have been good one, but we will convert it. This we will make it into liters. This you got 43.2 into 10 raised to 6 liters per day. You got. Okay, now see, interestingly, this is a sedimentation or coagulation tank, and the effluent is coming here. The coming effluent has a turbidity 37 mg per liter, and the effluent which is going from here, it is carrying 12 mg per liter. Then where that minus quantity goes? This is a sedimentation tank. Then this turbidity is coming and the effluent has 12 mg per liter. Means 37 minus 12 is 25. Then 25 mg per liter is settled down. Very important. 25 mg per liter is settled down. I will write it here. But here, if it is a sedimentation tank, this much is enough. But it is not sedimentation. Sedimentation aided, coagulation aided sedimentation tank. Therefore, when we add alum here, it will also produce some sludge, that is a flux, that is your aluminum hydroxide. है ना? Therefore that also settles down. But what is this quantity that I want? That I need to get it like 150 gram of flock. Now 1 gram of, we will make it kg now. Directly we will make it mg. Okay, we will call it as mg, and this also will call it as mg. Okay, now the dosage is how much? 23 mg per liter is the dosage.
Then 23 mg of alum produces X at X equal to 23 divided by 666 into 156. The answer is
5.38 mg per liter. This 5.38 is what? This is a flock, and this 25 is what? This is also sludge. Now these two will be added and we will get 30.38 mg per liter settles down. 30.38 mg per liter settles down. Then what will be the total sludge for per day? It is now 30.38 mg per liter into 43.2 mld, that is 10 raised to 6 liter per day. Then we will get 1.3124 tons. What? This much is settled at the bottom of the tank. But this 1.3124 is the sludge in solid. This is solid. Okay, here we don't have any water because everything is measured in mg per liter. Therefore 1.38 tons is a solid. But below the tank, when we want to remove, we don't get a sludge in a solid form. We will get a sludge in a somewhat liquid form. Therefore, in the problem itself, they have said that 1%, here it is 1% sludge content is there. Then what about 99%? Then 99% is water. Therefore, that we will use it here. That is we got 130 ton of water. Now water specific gravity is 1, therefore I can write it as 130 meter cube of water also. Meter cube of water. Okay, this I got. Now 1.38 ton of 1.31 ton of solids means how much volume it takes. For that, a specific gravity is given 3.01 and we will convert it into density. Its density becomes 3.01 ton per meter cube. This is a sludge density. Then that this equal to mass by volume. Then the volume equal to mass by density. Okay, then mass is 1.3124 divided by 3.01. The answer is 0.44 meter cube. This is a solid sludge volume and this is a water volume. both together we will call it as a liquid sludge. Now both together it is called as liquid sludge. Then what is a liquid sludge we got? Liquid sludge is 129.9 plus 130, we will take it 130 plus 0.44, that equal to 130.44 meter cube. Okay, this much we need to remove. Okay, the question, read the question. What volume? The question is, what volume of sludge must be disposed of each day? That is 130.44 meter cube of sludge must be disposed each day. Then based on your result, remark with reference to the treatment process. Means you need to tell that this is very huge amount of sludge and this much removing is very difficult, therefore we will call it as a thickener. Sludge thickener we need to use. So sludge thickener means what? Here in the thickener process we are going to remove the water and we are going to make dry solids there and we will remove it easily. 130.44 meter cube removal per day is very huge. Therefore suggestion is we should provide sludge thickener along with the treatment plant. Okay, na? Over. Now the problem number 5. Now we are entering into design of this flocculation and all, flocculation and sedimentation tank. Design the water depth for mixing basin having around the ends baffles. Okay, baffles. Okay, around the end baffles means plan, which is shown in the previous video. In order to treat 48 mld of water, the tank may be divided into three similar compartments by providing a longitudinal portion wall, and each half may have a clear width of 8 meter. Assume suitable value of detention time and the flow velocity through the basin. The clear distance between the baffles may be kept as equal to minimum permissible. Mention the number of channel in the tank and also overall inside length of the. Instead of three similar components, we will take it as a two similar compartments by providing. Okay, you should know what is baffle walls. It is, they are asking you mixing basin. Mixing basin, we have two types of mixing basin. The one is mixing basin with baffle walls and the second one is mixing basin with equipment, mechanical equipment, stirrer. Okay, but here this baffle valve only we need to use. And one more guidance, it is said that they asked us to design end baffle around the end baffles. Okay, means the flow is horizontal. Let us consider the water is coming like this and the baffle walls are like this. Okay, then the water comes like this and it takes a turn like this and it enters here. Then again here also baffle walls will be there. Okay, like this it is moving and it comes out. Okay, this is what a mixing technique. When they come here, when they divert here and there, then there will be turbulence creates there. Due to the turbulence, the mixing technique will be very easy. Okay, now the quantity given here is 48 million liter per day, and clear spanning and everything it is given 8, and suitable data we need to assume. Okay, first we will assume detention time. Here we will assume 30 minutes. 30 minutes. Why 30 minutes? Because the range for mixing device is 20 to 50 minutes. The range is 20 to 50 minutes is there. Therefore, I assume 30 minutes as detention time. That is your 0.5 hours. Okay. Now we need to think, if this is a tank, then in a half an hour, how much quantity it is coming? See, in one day, 48 into 10 raised to 6 liters are coming, but the entire water will not store in the tank. Therefore, only for 0.5 hour. Therefore, we will convert this one first into in terms of hour. 48 into 10 raised to 6 divided by 24 hours. Then 24 ones are 24 twos are. Okay. This much of liter per hour. We will make it into meter cube. Therefore, 2000 meter cube per hour. This 2000 meter cube per hour I want for half an hour only. Therefore, this will be 1000 meter cube. 1000 meter cube. What is this 1000 meter cube? This will be the volume of mixing tank. Mixing tank. Now we got one dimension. Volume of mixing tank, we got it. Any doubts? Now we will assume another data. The another data is flow velocity. Then the water which is allowed through this mixing device, in what velocity they have to move. The design says that it should be 0.15 to 0.45 meter per second. Then what we'll do? We will assume 0.3 meter per second. We will assume 0.3 meter per second. Then velocity equation we know, distance by time. Then the distance means what here? The length of a travel, length of water travel divided by time. Time is what? Detention time. That is 0.5 hours. I want in seconds. This becomes minutes and this becomes seconds. Therefore, the velocity is 0.3. Therefore, I got here length equal to 540 meters. Understood? This is not length of the tank. This is length of the water, because water is going in zigzag way, no? The water enters here and it goes like this zigzag way and it comes like this, then again it goes, and this entire length is 540. It is not a tank dimension. Okay, no? Now we need to do that. Tank dimensions we need to do. Cross-sectional area of tank. Sorry, cross-sectional area of flow. Cross-sectional area of flow. Flow cross-sectional area I want. If the water is going like this, then this cross-sectional area means what depth it will be having here. Okay, that I want. Therefore, that will be equal to, cross-sectional area will be equal to volume divided by length. That is 540 divided by length is how much? Sorry, 1000 divided by 540. The answer is 1.85 meter square. Okay, now 1.85 meter square it got. Now the distance between the baffle walls is kept equal to the minimum permissible. I will show you the diagram how it is. Now here, okay, this is a baffle wall and this is another baffle wall. Then the clear distance between the baffle wall, how much it is? Minimum, as per the guidance, it is 0.45 meter. Therefore we will consider the clear distance between two successive baffle walls equal to 0.45 meter. Now see here, When that water comes here and it goes like this, and this distance, it is y, and the y is how much? Y is 1.5 times x. Therefore, this y will be equal to 1.5 times x, that is 1.5 into 0.45, that is 0.67. We will round it up to 0.7 meter. Okay, now 0.7 meter, we got it. Water is traveling from here like this. When it comes here, just think here. I will take a red color. When it comes here, then it will be having its cross section. Then water will be going like this. Means here some height will be there. If I put a cross section here, then its width is 0.4. Then the height will be what? Something h. Okay. Then this is 0.45 and this height is h. Then what is the cross sectional area? Cross sectional area we already know, that is 1.85. okay, therefore L in that 0.45 into h equal to 1.85, therefore h equal to 1.85 divided by 0.45, answer is 4.12. Round it to 4.2 meters. Now you got means the height of the buffel walls will be more than 4.2 meters. Height of the buffel walls will be 4.2 meters. Okay, now how to get the length of the water? Because the length of the water is, it comes here and it goes like this, like this, like this, like this, like this. It travels all along this way, and we don't know how exactly we need to measure this one. Therefore we have a guidance here, that is effective length. Effective length we need to calculate it from this. It is given effective length of the channel is whatever the distance it is there, half of that one we need to take one mark, and here whatever the distance is there, half of that we need to take, and this much and this much if we reduce, whatever the length we are going to get, that is your effective length. Then at effective length we need to calculate. In the problem it is given 8 meter is the width. Okay, width of that means here in the problem it is given from here to here it is 8 meter, then half there and half here, means one opening will be reduced from that, then we got 8 minus, then effective length equal to 8 minus 0.7, this is your 7.3 meter. Okay, then how many lengths are there here? That zigzag we don't take this conversion, just 1, 2, 3, 4 like that. How many chambers will be there? That many effective lengths will be there. Or indirectly, I know the length, I know the total length divided by effective length, then I will get a number of chambers. That is your 540 divided by 7.3. The answer is 74 chambers you are going to get. 74 chambers. Then they said that 2 compartment we need to do, therefore each compartment will be having 32 chambers. 32 chambers. Okay, means from here, that is from here to here 32 chambers, and from here to here 32 chambers. Okay, 74 chambers will be there. Then what is the total length of the tank? Now you can determine the total length of the tank. You can see this figure. In this figure, this is drawn in AutoCAD by considering exact dimensions which are there in the design. Okay, Here these are your buffet walls, and this distance is 0.45 and this distance is 0.7. Okay, this is 0.7, this is 0.45. This is a plan. Like that, here you got 32 chambers and here you got 32 chambers. The water which comes here zigzag and it comes here and it enters into the second compartment and again zigzag and it will come out. Okay, this 32. Now if I want to calculate the length of this inner side length of this one, then how to calculate? That is very easy. 32 chambers are there and each width is 0.45. Each width is 0.45 plus there will be 31 baffle walls will be there, and each we are going to consider 7.5 centimeter. They will be very thin. Okay, 7.5 centimeter means 0.075 meter. Then this is your total width of the tank, total length of the tank. 32 into 0.45 plus 31 into 0.075, that is 16.725. It is 74 by 2. This will be 37 answer. Therefore this will be 37 compartment chamber, 37 chamber. Therefore this is 37 and this is 36. This is 19.35. 19.35 over. Okay, now you got the total overall length. It is 19.35. Then this length is how much? This length is 8 meter. It is already given. Then you can have the concrete wall here, then this again 8 meter, and the height is 4.2 meter. You can give a freeboard of 0.5 meter so that it becomes 4.75 meter. Okay, problem solved. Design the coagulation sedimentation tank with continuous flow type for a population 60,000 persons, daily 120 LPCD. I will make it very fast. See, the population is 60,000 and each person 120 liters. Therefore the total water is 60,000 into 120. This is the average demand and I will make it at a maximum demand. Therefore I got
12.96 mld. 12.96 into 10 raised to 6 liter per day. Okay.
Then make a suitable assumptions here. Then sedimentation tank, coagulation aided sedimentation tank. Therefore first I will assume DT, detention time. This detention time can be 2 to 4 hours. Therefore I will assume it as a detention time 4 hours. Then overflow rate V0 can be 1000 to 1250 liter per hour per meter square. Therefore I will assume 1000 liter per hour per meter square. It is nothing but meter per second only. Now how to design the total volume of the tank? In the last problem also explained, in one day this much water is coming, but the entire water will not be there in the coagulation tank, but only for the 4 hours that water will be there. This we will make it first in terms of per hour.
12.96 into 10 raised to 6 divided by 24. This is your 0.54 into 10 raised to 6 liter per hour. I will make it into 10 raised to 3 liter per meter cube per hour. Okay.
Now for 4 hours I want, therefore
0.54 into 4. This is into 10 raised to 3. This is 2.16 into 10 raised to 3 meter cube. This is the volume of the tank.
2160 meter cube. This is volume of the tank. Now volume is decided. Then what? You know V0. V naught equal to Q divided by BL. Q divided by BL. Q is how much? This Q equal to what? Meter cube per hour, no? Meter cube, how much meter cube we are going to take here? 2160 meter cube per hour is how much? 4 hour. That is 540. This is 540 meter cube per hour. Then V naught is assumed as 1000. This is liter per hour per meter square. Liter I will convert it into meter cube. Therefore 1000 liters means what? It is 1. That is 1 meter cube per hour per meter square equal to Q is 540 meter cube. This is 540 meter cube per hour by B into L. Then it equal to 540 meter square. Now you can assume B equal to 12 meter.
And assume B equal to 12 meter. Then find L equal to 540 divided by 12, 45. L equal to 45. Then you know the volume.
Then you can find out H. H equal to 2160 divided by 12 into 45. That is 4 meter. Then for sludge you can give 0.5 meter bottom and 4 meter for clear water, and 0.5 meter you can give the freeboard. Therefore the total height will be 5 meter. Over height is known to you, length is known to you, and breadth is known to you. This problem is homework for you people. Okay. This is your time. Solve many problems from other textbooks, and if you have any doubts, give a comment, or otherwise you can call also. Thank you.